Right, so welcome everyone to this new video where we discuss things mathematics or physics on the board. Here actually it's a video where we are going to talk about some aspects of mathematics and also some aspects of physics, so all kind of in one go. So the thing that we are going to see is basically that there is some mathematics that is very useful to shed light on how to view let's say the notions of absolute temperature and entropy in thermodynamics. Right, okay, so to try to illustrate the problem we want to look at in the first place, the idea would be to look at a one form, so it's a one differential form that I've completely made up, okay? And what we want to know is basically is omega integrable, sorry, not differentiable, but integrable. And so what we mean by integrable here, we want to ask whether omega is equal to some d of f, where d is the exterior derivative. Okay, so if you don't remember what the exterior derivative is about, so by the way, let me check. I think I can switch on the light. I don't know if it's better, but what the exterior derivative is about, I will put some link somewhere for you to check again, okay? But essentially this is a typical, like a new kind of derivative that is used in exterior calculus. Now, let's have a look at what, one way to actually look at this is that if omega is equal to df, then we have that d omega is equal to df, and that's equal to 0. And that's by definition, if you apply twice the exterior derivative, then you're going to get basically 0. Okay? Sorry, I need to check that a bit. So that's the idea. So let's have a look at what d omega is equal to. So d omega is equal to d of x, y, z wedge dx plus d of x squared z wedge dy, and then plus d of x squared y wedge dz. So here what we need to replace it with is essentially the derivative or total differential of the function, the scalar function x, y, z here. So that's going to be yz dx plus xz dy, and then plus xy dz, and that's wedge dx. Here we are going to get plus 2xz dx, and then plus x square dz. There is no y, and so wedge dy, and finally plus, here this is the term, so 2xy dx plus, where are we, x squared dy, and then this is wedge dz. So now what I need to remember is that dx wedge dx is 0. Likewise, dy wedge dy is 0, and dz wedge dz is 0. So all of these guys kind of cancel out, and so in the end what I'm getting is I've got x z dy dx plus xy dz wedge dx. Then finally we've got, finally no, we're not there yet, plus 2xz dx wedge dy, and then plus x squared dz wedge dy, and then plus 2xy dx wedge dz, and then plus x squared dy wedge dz. Now, what I can do is actually make these things a bit more compact. And the way I do that is basically noticing that dy dx is equal to minus dx dy, that dx dz is equal to, where is it? Here, is equal to minus dz dx, and so on and so forth. So that's what I'm going to do on that side. So I've got that d omega is equal to, so I'm going to factorize here dx dy, and then dx dy we've got minus xz, so hold on, let's take this one. So it's 2xz minus xz. So actually this is times xz. So let's write it then directly with xz. So we've got xz, and then which one was it? dx dy. Then let's say we've got a plus here, and that's going to be, let's say, dz dx. So dz dx, we've got xy here, and here we've got 2xy. And so we need to swap that, so actually there's going to be a minus. So that's minus xy, and then dz dx. So again, I can put it a bit closer to me. So minus xy dz dx. And then finally, we have the dy dz. Okay? And dy dz here is going to cancel out. So you've got x squared dz dy, which is minus dy dz, and so they are going to cancel out. So d omega is equal to that. So what we see is that this is different from 0, and therefore we've got that omega is not, let's say, ideally integrable. Okay, so that would be ideally, so it's not kind of ideally, it's not the ideal case of integrability, integrable. So what do we do with this? Well, it turns out that there is a way to fix it and to generalize a little bit the meaning of integrability, and this is related to a theorem by Frobenius. So let me write this like this. So there is a way to fix a non-integrable or non-exact differential equation like this, or at least differential like this, and so which is as follows. You've got Frobenius theorem, and here there's just a simple version of it I'm going to say, so Frobenius theorem. And this theorem says that if you can have that omega wedge d omega is equal to 0, then you're going to have, so if omega wedge d omega is equal to 0, then you're going to get that omega, then there exists, I think that's really the important part here, then there exists two functions, f and g, such that omega is equal to g df. Okay? So, so that's the idea. So what we want to check now is whether or not, so that's a theorem, and I want to check whether or not, and this by the way is called integrable as well. Okay? At least locally integrable. So that's kind of the idea. So what we want to check now is we want to look at what omega wedge d omega is equal to. So we've calculated d omega there. So we can simply take the wedge. So omega is all of that. That's x, y, z dx plus x squared z dy plus x squared y dz. So this thing is omega, and then wedge this stuff here. So that's simply xz, and then dx dy, and then minus xy dz dx. Okay, so remember that dx wedge dx is 0, dy wedge dy is 0 as well. So it's actually very easy to get plenty of 0 terms, and the only non-zero terms that are going to come are basically this dy with this term here, and this dz with this term here. There are only 2 terms that are non-zero. And so let's do it. So here we've got x squared. So we've got, in fact, directly minus x cubed, and then yz, and then dy wedge dz dx, and then we've got plus x cubed yz, and then dz wedge dx dy. Okay? So now what we do is something that we've done in some other video. If you want, I can provide a link here. This is something we looked at for calculating Hodge duals. But the bottom line is that you need somehow to get the dx here. So you can basically swap this. So that's a number 1 swap, and you're getting a minus sign. And then once you've got the dx there and the dz, then you want to do, as a second step, you get another minus sign here. So let's put in circle the number of the step, and basically the minus sign here. So the bottom line is that you've got 2 swaps to do, and therefore you just multiply by minus 1 times minus 1, which is plus 1. And here actually the same thing will operate. So you first basically get this dz with this dy, for example, so that's the first step, and you get a minus sign from it. And then once you've got the dy here, you swap with the dx here. And you get again a plus 1. And what you end up with is basically minus x cubed yz plus x cubed yz, and then times the volume form dx dy dz, and that's equal to 0. So the bottom line is that from this particular theorem, we see that the solution, like this problem of integrability, can be salvaged, right? There is a way to actually find some function f and g such that omega can be expressed in that fashion. And so I'm not going necessarily to make you kind of try to figure it out. There are ways to try to do that via equation solving, but that's not the point here. What I can tell you is that actually here omega turns out to be equal to x df, and then f. So let me say that a bit differently. You can check for yourself that actually solution is omega is equal to g df, where g is equal of x, y, z is actually equal to simply x, and then f of x, y, z is equal to the product of x, y, and z. Okay? So you can check that this is the case, and therefore from there you basically have something which is integrable. And again, this integrability aspect comes from simply the fact that you can write it in this fashion. So what that means is that you've got a term df that can be expressed as omega over g, right? So you do have an actual kind of total differential that can be defined in that case. Now, that's the example I wanted to show. So what I wanted to show is that if you've got a non-exact form, one form in particular, if you've got a non-exact one form, you can, in some circumstances, actually make it into an actual, introduce, let's say, a total differential, okay, to salvage things. So now what I'm going to do is that I'm going to erase this particular kind of board, and then we are going on to thermodynamics. Right, okay, so now let's actually talk about the thermodynamics aspect. Of course, I will talk more about these aspects, but here this is just to show some very specific principles that come to the fore. So here on the very top, I simply wrote like a general formulation in the so-called quasi-static regime. So for very slow processes going on, you've got that du, the infinitesimal variation in the internal energy, is equal to delta W plus delta Q. So delta W is a work that is being received or done by the system depending on the convention you use, and delta Q is a heat being received by the system. Now often the work is considered as, like through the definition of work, as a sort of forces that are acting on the system, and here these are some kind of thermodynamic variables that are relevant to characterize your thermodynamic system. Now usually this would be something as simple as, for example, minus P dV or something like this, okay? So pressure and then times dV, where dV is a variation in volume. So that's something quite common. Now what you can do, so that's from the first law. Now what you can do is simply invert that to express delta Q as being this. So delta Q in that case is expressed as a one form. So that's why I wrote omega. So omega is a one form, and as it turns out, what people observed experimentally and so on, that this omega, this delta Q, the heat, turns out to not be exact. Okay, so it's not an exact one form, so I can't express it in the same way I do with, for example, the internal energy, where I can express it as a total differential. So basically as the exterior derivative applied to a function. So basically I can't do that with delta Q, and I can't do that with delta W, by the way. However, the thing is that one of the things is that we want to essentially try to express delta Q in a fashion that is similar to this one, okay? But maybe even actually better. And this is actually a work that was proposed by Caratheodory, and in fact this is Caratheodory theorem. And the theorem goes as follows. It says that if you have, the theorem goes, two steps to it, is that there are states called B, for example, thermodynamic states B, that are close, that are arbitrarily close to states, to an arbitrary state A, which cannot be accessed by an adiabatic path. And adiabatic means, by the way, that delta Q equals 0, path between the 2 points. Okay, so that's kind of the first statement. It's called sometimes Caratheodory's principle or axiom. And then actually it follows from that if, so let's say this is premise A and this is B, so if A holds, then essentially we've got that delta Q, so I'm going to write actually, yeah, well I can write it this way, delta Q d delta Q is equal to 0. And here I basically bring you back to this. So it basically tells you that we are in the context of Frobenius theorem, and so if we are in this context, it means that we can write omega, which is delta Q, in a form, so it follows from this that there exists, and essentially that's the definition that Caratheodory gives to this. There exist two functions, which are here t and s, such that, and then you've got that delta Q is equal to t ds, and basically meaning that delta Q is integrable via an integration factor that you would call t, and then you've got this particular ds here, which is a function of state. Okay, and so that comes from this particular assumption and the mathematical equivalence of that assumption with essentially Frobenius theorem. Okay, and so that's how Caratheodory essentially introduced the entropy and the absolute temperature. So this stuff here is the absolute temperature, and in fact, so that's the absolute temperature. And this thing here is the entropy. And they are interpreted as kind of a multiplicative factor. And the thing that I'm not showing here, but that Caratheodory and some other authors, of course, have defined, is basically they show that this absolute temperature only depends on the empirical temperature. It does not depend on the other thermodynamic variables like pressure and so on, at least as far as the kind of scale is concerned. Okay, of course there is dependence via equation of states, but here the way they appear in that expression, it only depends on the empirical temperature. Okay, any other kind of dependence is going to be connected to this other function there. Alright, so basically this is just to show you the deep connection there is between differential equations, exterior calculus, one forms, and basically thermodynamics.